Hi, today we're going to talk about what randomness is and a bit about how computers imitate and use randomness.
I'm Monica, a third-year computational biology PhD student at CMU. My research focuses on analyzing the spatial patterns of microscopy images of human tissues to improve clinical predictions.
And I'm Roshni. I'm a third-year computational biology PhD student at Pitt. My research focuses on using protein dynamics to improve drug discovery. So, what exactly is randomness? You've probably seen random events before, like the shuffle function on your music app or a secret prize at an arcade claw machine. What these events have in common is that you can't predict their outcome. The next song or the toy in the box could be anything, or at least anything within what we call the space of possible outcomes. In the shuffle function example, this space would include all of the songs on your playlist. The next song could be any of these, and you can't predict which one. And if you left the shuffle function on for a whole day, you wouldn't be able to find a pattern in the songs it chose to play. An important aspect of randomness is the probability of each outcome occurring. While we can't predict what the next outcome will be, we can figure out what the probability of each outcome is. In random selection, the probability of an outcome, A, is related only to the proportion of A in the space of possible outcomes. We see this a lot in the tools we use to make random decisions, like flipping a coin or rolling a die. These proportions have a 1 in the numerator, since each outcome only appears once. On a coin, the chance of getting heads is 1/2, as is the chance of getting tails, since there's only one head and one tail on the coin. Similarly, with a 6-sided die, each number 1 through 6 is only represented once, so the chance of each number being rolled is 1/6. Of course, assuming the coin and the die are totally fair. What this means is, if you roll a die a large number of times, you'll get each number on the die roughly 1/6 of the total times you rolled it. But there are situations where each possible outcome is not represented equally. You can still have random selection in this case. Let's consider a bag of candy. If you have candy at home from Halloween, you can use that too. Just make sure you have a variety of different types. The possible outcomes of selecting from a bag of candy could be, for example, chocolate, like Hershey's, fruity, like Starburst, sour, like Sour Patch Kids, or nutty, like Snickers. There are definitely multiple types of candy that could be in each category, and there are probably more of one type of candy than another, like if a lot of your neighbors gave out Starburst this year. For this exercise, though, we're going to make sure we assign the categories such that every piece of candy is only in one category. Even if you have a Snickers, it's either chocolate or nuts for our purposes, not both. In random selection, there's still an equal chance you pick any single piece of candy from the bag. What changes is the proportion of the outcome represented by that piece. So if you have 10 starbursts in the bag, with a total 20 pieces of candy, the probability of picking any single piece, including the starbursts, is 1 out of 20. But the probability of picking a fruity candy becomes 1/2, since there are 10 fruity candies out of the total 20. Let's try with your candy. Count the number of candy you have for each of the 4 categories. Let's call each of these numbers by a name. NC for chocolate, NF for fruity, NS for sour, and NN for nutty. Our total number of candy, all of these small n's added together, we can call big N. You can use a table like this one to keep track of all of the numbers in your candy bag or in the image on screen in the next slide. Let's say you pick a piece of candy out of the bag without looking. Make sure you don't feel around for your favorite candy either, then it wouldn't be random. Just shake up the bag and pick the first one you touch. First, what's the probability of picking any piece of candy randomly out of the bag? Pause here to figure out the answer. To pick any one piece of candy, you need the proportion of one piece to the total number of pieces. Since there are n total pieces, this is 1 over n. If you randomly select one piece, there's an equal 1 over n probability of it being any piece in the bag. Next, what's the probability of picking each of the 4 outcomes randomly out of your candy bag? Pause here to figure out the answer. To pick any one outcome of candy, you need the proportion of one outcome to the total number of pieces. Think back to when you counted out each type of candy. There's more than one piece of candy that satisfies the outcome of chocolate or nuts, and so on. This is each of the small n's. And on top of that, the small n's aren't all the same. So for chocolate candies, with NC, chocolate, and total candy, the proportion of the chocolate outcome would be NC over N. We can do the same for any of the outcomes. Finally, if you wanted to make sure there was an equal chance of randomly picking each type of candy out of the bag, what would you do? Pause here to figure out the answer. We saw earlier that for a random selection, the only thing that matters for which type of candy you pick is the proportion of that type. So if there's more chocolate in the bag than nuts, you're more likely to pick chocolate on your selection. What if you want the chances to be even? What you can do is add or remove candy from the bag until all of the small n's are equal to each other. Then the proportions and probabilities all become n small n over big N for each type of candy. It's important to keep in mind that for a random selection, the proportion tells you just the probability that you'll pick that type of candy once. Let's say you replace each candy you pick, shake the bag up again, and pick another piece 10 times. Even if you pick chocolate 4 times in a row, you can't use that to predict what will be next. There could be 10 chocolates in the bag, making it more likely to pick that, or there could only be 2. It doesn't get more or less likely the more times you do it, as long as you are replacing the candy so the proportions don't change. That's what makes it random. There might be a fixed probability of each outcome, but you still can't know for sure which one it will be. So we know about how flipping a coin, rolling a die, or picking a piece of candy out of a bag can be examples of random selection. These also represent something called random processes, which are a sequence of events or samplings that can't be predicted and don't follow a pattern. Each flip of a coin or roll of a die depends on just the distribution of outcomes, in this case, a uniform distribution, since every outcome has the same probability, and not on the previous events. So for multiple dice rolls, a distribution might look something like this. And if you kept it going even longer, rolling the die 100 times, it would keep evening out. Eventually, the bars counting the rolls would all be the same, or uniform. There are a lot of examples of random processes in nature, too. For example, movement of clouds and weather patterns in the atmosphere, or how the blobs move around in a lava lamp, could be represented as random processes.
What if we wanted to be able to model a random process with a computer? For example, what if we wanted to use a computer to choose a random song from your favorite playlist using shuffle, or perform a random coin flip, or to choose a number randomly between 1 and 10? Well, in order for computers to perform any task, we need to provide them with a set of instructions using code. But how do we tell a computer to be random? Well, we can do this with a type of algorithm called a pseudo-random number generator. Pseudo meaning having a close resemblance to or pretending. Computers can use pseudo-random number generators to simulate a real random process.
I'm going to give you an example of a pseudo-random number generator. Let's start with the number 8. Our goal is to generate a pseudo-random number using an initial number 8. To do this, we will need a couple of other numbers to perform operations with. Let us define a multiplier, adder, and a divider number. We can choose any numbers for these values, but here we will use 4, 1, and 9 respectively. To proceed, we start by using the multiplier number 4. 4 times 8 is 32. Then we use the adder number, which is 1. We add this number to the previous result, 32. 32 plus 1 equals 33. Then we use the divider number on the previous result. What is 33 divided by 9? Well, 9 times 1 equals 9, 9 times 2 equals 18, 9 times 3 equals 27, and 9 times 4 equals 36. 33 is between 27 and 36, so we know that 33 divided by 9 equals 3, with a remainder of 6, because 33 minus 27 equals 6. The process of getting the remainder of a division problem is called the modulus operator,
or mod for short. So instead of saying 33 divided by 9 equals 3 remainder 6, if we only want the remainder, we can say that 33 mod 9 equals 6, and this final result, 6, is our first pseudo-random number from this generator. To recap this process, first we start with an initial number 8, then we multiply it by our multiplier number 4, then we add our adder number 1. Finally, we use the modulus operator with our divider number 9. The final result is 6, and this is our first pseudo-random number. To generate another pseudo-random number, we can repeat this process as before, but using the number 6 instead of 8. We will keep our multiplier, adder, and divider numbers the same. Again, multiply with our multiplier number 4. 4 times 6 is 24. Add our adder number 1. 24 plus 1 is 25. Then mod with our divider number 9. 25 mod 9 is 7. This is because 25 divided by 9 equals 2 with a remainder of 7. And so 7 is our second pseudo-random number. Let us repeat this process again to get our third pseudo-random number. 4 times 7 is 28. 28 plus 1 is 29. And 29 mod 9 is 2. And again, this is because 29 divided by 9 is 3, remainder 2. And so our third pseudo-random number is 2. For our fourth pseudo-random number, 4 times 2 equals 8. 8 plus 1 is 9. And 9 mod 9 equals 0. And this is because 9 divided by 9 equals 1 with remainder 0. 0 is our fourth pseudo-random number. And we can continue to repeat this process over and over again to generate more numbers. To summarize the entire process, we first started with an initial number 8. We can also refer to this as our seed, which we can denote with the symbol x0. Then we have our multiplier, adder, and divider numbers, which we can represent using the letters A, C, and M. A, C, and M are just symbols representing these numbers, in which our case are 4, 1, and 9, respectively. To generate our pseudo-random numbers, we multiply the seed with our multiplier number, add our adder number, and take the mod with our divider number. And we continue to repeat the process with the new number, as shown here. Here, our first 4 pseudo-random numbers are 6, 7, 2, and 0. To make our notation a bit more organized, we can use symbols in our equations instead of numbers. Our first pseudo-random number we can call x1. The second number we call x2, and so on with x3 and x4. Again, these symbols just represent the numbers we had before. Now, remember how we said we could call the multiplier number A, the adder number C, and the divider number M? Well, we can write each of these equations using those symbols instead. So, for this first equation, we have A times x0 plus C mod M equals x1. The next equation is A times x1 plus C mod M equals x2. And we have similar equations for x3 and x4. Do you see a pattern here? The only thing we are changing on each line is the number of x that we are using. To rewrite this more generally, we have A times xn plus C mod M equals xn plus 1. The symbol xn represents the result of the previous equation, and xn plus 1 represents the result of our current equation. An equation like this, where the value of xn plus 1 requires the previous output, xn, is called a recurrence relation. And this specific recurrence relation is called a linear congruential generator. To create a sequence of pseudo-random numbers with the linear congruential generator, all we need to do is define A, C, and M, which we can call the parameters, and the initial seed, x0. In the example I just walked you through, we had x0 equals 8, A equals 4, C equals 1, and M equals 9. This produced the sequence x1 equals 6, x2 equals 7, x3 equals 2, and x4 equals 0, and so on. Note that if we started with a different seed or initial value, x0, we would get a different sequence. Let x0 equal 7 this time, with the same parameters as before, a equals 4, c equals 1, and m equals 9. What are x1, x2, and x3 this time? Pause here if you want to try this yourself. The answer is x1 equals 2, x2 equals 0, and x3 equals 1. Note that x1 and x2 are actually the same as x3 and x4 in our first example. This is because we started with 7 as our initial seed, which is the same as x2 in the first example. This shows that the linear congruential generator is not truly random, only pseudo-random, because if we have the same parameters and the same inputs, we will produce the same sequence order. Now let's try another example with different parameters. Let a equal 6, c equals 8, m equal 10, and x0 equals 7, our seed. What are x1, x2, and x3? Pause here to try this yourself. The answer is x1 equals 0, x2 equals 8, and x3 equals 6. Now, we've discussed how the linear congruential generator works and how it produces pseudorandom numbers given the parameters a, c, and m, and an initial seed, x0. And if we plug in different values for these parameters and the initial seed, we obtain different versions of the generator. But how can we use the generated numbers to simulate a random process, like a coin flip? Well, first, let me note that the range of random numbers produced by this generator depends on the parameter m. If m equals 5, then the range of numbers we can generate is 0 through 4. If m equals 10, the range of numbers is 0 through 9. To demonstrate this observation, try 5 mod 5. This equals 0. 6 mod 5 equals 1. 7 mod 5 equals 2. 8 mod 5 equals 3. 9 mod 5 equals 4, and 10 mod 5 equals 0 again. So, the largest number we can get using m equals 5 is 4. And more generally, the largest number we can get using the parameter m is m minus 1. Here, I'm showing the first 3 pseudorandom numbers from my last example. If we divide our sequence of pseudorandom numbers by m minus 1, we will get a decimal value between 0 and 1. Let us take our last example, where a equals 6, c equals 8, m equals 10, and x0 equals 7. Here, m minus 1 equals 9. This means that the range of numbers we can get is 0 through 9. The first 3 pseudorandom numbers from this generator are 0, 8, and 6. Dividing each of the generated numbers by 9, we get 0, 0.889, and 0.667. And so, to simulate a random coin flip, we can say if this divided result, this decimal value, is greater than 0.5, we have a heads. If the result is less than 0.5, we have a tails. So in this specific example, we flipped tails, heads, heads.
As I demonstrated, the linear congruential generator will produce a different pseudorandom sequence for each set of parameters and seeds. One common set of parameters used by computers in practice is shown here. A equals 8,121, C equals 28,411, and M equals 134,456. So if we start with an initial seed of x0 equals 123, we get the sequence x1 equals 86,102, x2 equals 91,553, x3 equals 123,100, x4 equals 43,151, and so on using this recurrence relation. But if we start with a different initial seed, we will get a different sequence. So if x0 equals 0, we have x1 equals 28,411, x2 equals 27,646, and we can continue with x3 and x4 and so on. And so we have with different seeds but the same parameters, we will get different sequences. And like before, we can simulate a coin flip by dividing these numbers by n-1. Here, n-1 equals 134,455. And if we divide these sequence values by this number, we will get these decimal values between 0 and 1. And again, if the result is greater than 0.5, we flip heads. If the result is less than 0.5, we flip tails. And so here, we flipped tails, heads, 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 tails. The linear congruential generator is just one example of a pseudo-random number generator. Another pseudo-random number generator that is most commonly used in today's computers is called the Mersenne twister. And if you want to learn more about that, check out the link in the description. We've talked about what randomness is, examples of random processes like dice rolls and shuffling songs, and an example of how a computer can mimic a random process using a pseudo-random number generator, specifically the linear congruential generator. Now, I'm going to show you how to create random drawings using code. Click the link in the description or enter the link on the screen as shown here. This should bring you to a page that looks something like this. On the left, there is some Python code. Don't worry if you're not too familiar with coding, I will walk you right through it. On the right, there are some instructions that you can refer back to after watching this video. Clicking the Result tab on the right will bring you to a panel where the result of our code will appear. And on the top left, there is a button that says Run. If we click Run with the current code, we get this animation on the right. Try doing this yourself. What we're seeing is a turtle repeatedly drawing 10 white swirls, starting in the same place but at slightly different angles each time. And if we click Run again, we're going to get the same image. Now, we see that this isn't random. We know what image we're going to get based on this code. But how can we incorporate randomness here? Can we, for example, choose a random color for each swirl? How about location? Can we change the code so that the turtle starts each swirl from a random location in this window? Can we also randomly choose the size of the swirl? Some of them could be small, some of them could be big. Well, first, before I show you how to do that, I'm going to walk you through this code so you know how the code is drawing this image. First off, all the lines that are green or that have hashtag or pound symbols at the beginning, like in line 5, are called comments, and they do not affect the function of the code in any way. They're just a way for me to describe how the code functions in text and also just to make some notes. The first two lines here with import are importing specific Python coding packages. The package turtle allows us to draw lines and curves using code. The package random allows us to use pseudo-random number generators to generate random numbers, like we discussed in the previous section of this video. Lines 6 through 8 are defining our window to draw in. We set it up so that the position 0, 0, or the origin is actually at the center of the window, and the horizontal and vertical directions span from -400 to 400. We also set the background color to black, but feel free to change this color if you'd like. Line 11 is creating a list of colors that we would like to use to draw our swirls. You can add or remove any colors here. Just make sure to put the colors in quotes with commas between them, as shown here. Line 14 is defining and naming our turtle. I decided to name this turtle Mochi, but you can name yours whichever you want by changing this name here, and also changing all the other times Mochi appears in the text. Line 15 sets the speed of the turtle. 0 is actually the fastest speed we can choose here. If you want to make the turtle a little bit slower, change the speed to 10. I'm going to keep it at 0. Line 16 sets the shape of the turtle to actually be a turtle. You can also change the shape to be an arrow, or a circle. And if I do circle, we have a circle instead of a turtle. but I'm going to keep it as turtle for now. Lines 19 to 21 define the function swirl. A function in code means a piece of code that performs some task. And in this case, the function swirl draws a swirl, given a specified size and length. Line 24 defines the number of spirals to draw. Currently, this is set to 10, but you can change this to be less or more. Just don't make it too high of a number, or else it would take a long time for this turtle to draw that. Line 26 defines a section of code that we call a loop. Essentially, what this does is allows us to repeat this next section of code over and over again. And since we want to draw swirls, this section of code draws our swirls. And so this is saying we repeat drawing swirls num spirals times. And num spirals times in this case is 10. So we set up this loop to run 10 times. Line 31 defines the color of the swirl. Note that it's currently set to white, as we see in the drawing. Lines 36 and 37 define the location of the starts of the swirls. Here, this is set to x equals 0 and y equals 0, which correspond to the center of the drawing. Line 40 tells the turtle to move to positions x and y, and line 41 starts the drawing process. Lines 45 and 46 define the size and length of the swirl. Right now, they're set to 10 and 100 respectively, which gives us this size swirl that we see in the drawing. Line 50 uses the swirl function that we defined earlier in lines 19 to 21 here. This draws the swirl. The lines 27 through 50, like I said before, are repeated the number of times as num spirals is set to, in case 10. Now, it is in this last section of code where we can incorporate the randomness into each swirl. Line 31 defines the color of the swirl. We see here that the color is set to be white. This is why each of the swirls in the drawing are white. But what we want to do instead is choose a different color of swirl from this list of colors that we have defined in line 11. And to do this, we need to use a function from the random package. The random.choice function allows us to choose randomly from a list. So we have this list colors, and we want to choose a random color from this list. And I'll show you how to use this function in code. So instead of setting our color to be white, we can set it to be random.choice, and then we want to choose a random choice within the list we called colors in line 11. So we'll do random choice colors. And this will give us, instead of setting the color of the turtle to be white, we set it to a random color within the colors list defined above. And so for each swirl, the possible colors that it could be set to are red, orange, yellow, lime, cyan, magenta, white, and pink. Change lines 31 in your code using this function and click Run to see what happens. You should get a drawing that looks something like this. It probably won't have the same colors that I'm showing here, because each time a swirl is drawn, it chooses a random color randomly from the colors list. But now you should note that not all of the colors are white for each swirl. Great. So now the drawing that you've just produced is a random drawing. Each time you click Run, you're going to get a slightly different output. But all of the swirls are still in the same location as before. What if we wanted to choose random locations for each of the swirls? Well, there's another function from the random package that is called random.randint that allows you to choose a random integer number between a certain range of numbers. To change the locations of swirls, we need to change lines 35 and 36, the values of x and y. Here they are currently set to 0, but we want to change them so we can randomly choose any coordinates within the window. So let's just choose random coordinates between the values of -350 and 350. And so to do this, instead of having x equals 0, we can say x equals random.randint, like so, negative 350, positive 350 within the parentheses. And so what this is doing, it's choosing, instead of choosing just 0, it's choosing a random number between the values negative 350 and positive 350. And so we want to do the same thing for y. Great. So I want you to change these lines 36 and 37 as I've just done here. And when you're done with that, click Run. You should see a result that looks something like this, or actually probably something that doesn't look like this, because now we have randomly colored and randomly located swirls. And to make this drawing even more random, we can randomly select the size and length of the swirl. Note that all of these swirls are the same size at the moment. And so to do this, we need to change lines 45 and 46, which define the size and length. These are currently set to 10 and 100 respectively, but let's change the size number to be a random number between 5 and 50. So we want something between 5 and 50 here. And we want the length to be a number between, say, 50 and 250 here. I'll let you try to change this yourself. Here's a hint. Use the random.randint function like we did in lines 36 and 37. And pause the video here while you write these lines of code. If you wrote the code correctly, you should be drawing swirls of random colors, shapes, and in random locations. If you're getting error or your code isn't running properly, make sure you have the same lines as I'm about to write here. Line 45 should have random.randint between 5 and 50. Length should be random.randint between 50 and 250. So when I click Run, I'm going to get swirls of different lengths, different sizes, different colors, and at different locations. And so now you can draw random swirls with Python code. And if you ever want to play around with the code later, you can return to this web page whenever you want. The instruction panels on the right side should guide you through using the random functions.
Remember the shuffle function example? That's just one way that computers use pseudo-random number generators. Computers use random numbers for everything from video games to scientific computing. Minecraft uses random numbers to set up each new world, and you can even set the seed yourself if you want to know exactly how it'll go. Computers even sometimes look to randomness in nature to generate random numbers that are a little less predictable than a pseudo-random number generator. LavaRand is a random number generator that uses bubbles in lava lamps as a seed, so there's a little bit of extra unpredictability thrown in at the start. Randomness is really an integral part of our world. Look around. What examples of randomness can you find in your life? We hope today's lesson helps you understand them a little bit better.